Hi, everybody. It's Professor Mitchell. We're continuing Chapter 2 today on polynomial and rational functions. And today we're going to be talking about quadratic functions. In this section, we will recognize characteristics of parabolas, graph parabolas, determine a quadratic function's minimum or maximum value, and then solve problems involving a quadratic function's minimum or maximum value. So first we'll look at the standard form of a quadratic function. The quadratic function f of x equals a times x minus h squared plus k, where a does not equal 0, is in standard form. The graph of f is a parabola whose vertex is the point hk. So this goes back to section 1.6 from the previous chapter. I believe we looked at the graph of the basic quadratic function f of x equals x squared. And if you remember the rules from that section, let's start off by assuming that h and k are positive, just to make it a little simpler. Replacing x with x minus h would shift the graph h units to the right, and then putting the plus k on the end of the function would shift the graph k units up. So the vertex, which is in this case would be a low point, would start at the point 0, 0. This would shift at h units to the right. This would shift at k units up. So it would end up at the point hk. And then the number a, remember that if a is a positive number, that will cause the graph to be stretched or shrunk vertically. And if a is a negative number, it will also cause it to be flipped upside down. Okay? So the parabola is symmetric with respect to the line x equals h. Remember, that's a vertical line. If a is greater than 0, the parabola opens upward. And if a is less than 0, the parabola opens downward. And I can't resist showing you this really cute way. I wish I could say I made this up. Cute way to remember that, which is if a is positive, the parabola opens up. And if a is negative, the parabola opens down. Okay, so hopefully that makes that easier to remember. All right, let's see. Get my mouse back here. Okay, so the steps to graphing this function. First, determine whether the parabola opens upward or downward using what we just talked about, the value of a. Next, determine the vertex of the parabola, which is h comma k. Then find any x-intercepts by solving f of x equals 0. The function's real zeros are the x-intercepts. So we're getting a little ahead of ourselves there with the vocabulary. The zeros of a function are the numbers that make the function equal 0. And we're going to be talking about that more later in this chapter. And of course, this will make more sense when we do an example. Number 4, find the y-intercept by computing f of 0. Remember, to find a y-intercept, you always set x equal to 0. And then take all that information, the intercepts, the vertex, and additional points as necessary. Connect these points with a smooth curve that is shaped like a bowl or an inverted bowl. So for example, we have the quadratic function f of x equals negative x minus 1 squared plus 4, and they want us to graph that using the steps that we just talked about. All right, so first of all, the value of a is right here. Think of that as a negative 1, and because that's negative, the parabola opens down. The vertex is 1 comma 4. You have to be careful with this a times x minus h squared plus k. There is a minus built into that formula right here. So if x minus 1 is standing in place of x minus h, that means h is 1. It is not negative 1. Okay, but the k does not have a minus built in front of it. That would just be k equals 4. Okay, the x-intercepts are x equals negative 1 and x equals 3. I'm going to show that to you on the tablet. And while I'm there, I'm also going to show you that the y-intercept is y equals 3. So let's switch over to the tablet. Okay, so first we're finding the x-intercepts, then we're going to find the y-intercept. So to find x-intercepts, you set the function, which is negative x minus 1 squared plus 4 equal to 0. So let's see. Well, I guess I'll just do this. I'll subtract 4 from both sides, and that'll give me negative x minus 1 squared equals negative 4. We have a negative on both sides, which we can get rid of. That's going to give me x minus 1 squared equals 4. So now the easiest way to solve this quadratic equation is using what's called the square root property. If the square of x minus 1 is 4, then that means x minus 1 has to be either the positive or negative square root of 4. That's called the square root property. So that means x minus 1 is either positive or negative 2. And when I add 1 to both sides, I get 2 solutions, which are 2 plus 1 equals 3, or negative 2 plus 1, which is negative 1. So that explains what you saw in the presentation. The two x-intercepts are x equals 3 and x equals negative 1. That brings us to the y-intercept. The function was f of x equals negative x minus 1 squared plus 4. And I think you've seen me do this before. I am going to leave the x out of it and replace the x with a 0. So then that is going to give me negative square of negative 1 plus 4. The square of negative 1 is 1, but this negative sitting out front flips it back to negative. So this is negative 1 plus 4, which is 3. Okay. Now, I've got the graph all done out in the presentation. I'm going to try to draw it for you on the tablet. Just a word of caution, it's not going to be pretty, all right? My handwriting is actually much, much better than it looks on the tablet. The tablet's a little tricky to write on, but I'm going to do my best. Okay, so let's see. See if I can remember all that. What we found, I think I do. Okay, so the vertex was 1, 4. The x-intercepts were negative 1 and 3, and the y-intercept was 3. And remember that the parabola is symmetric through this vertical line that goes through the vertex. Okay, so what that means, for example, is see the point 0, 3 on there? That means the mirror image of that point is also going to be on this graph right here. And that gives me a pretty good idea of what this parabola looks like. Let's see. So the left side's going to look something like that, and the right side is going to look something like this. That's actually a little better than I was afraid it was going to look. All right, but it looks really good in the presentation because I used the computer to do it. So let's switch back to there. All right, and there it is. That is the graph of this quadratic function. All right, now let's talk about the case where the equation is not written in standard form. Consider the parabola defined by the quadratic function f of x equals ax squared plus bx plus c. The vertex of that parabola is given by the point negative b over 2a, f of negative b over 2a, all right? So in other words, you use the formula negative b over 2a to find the x coordinate of the vertex, and then plug that value back into the function to get the y coordinate. And of course, we're going to do an example. The x coordinate of that point is negative b over 2a. And, oh, this is what I just said, right? The y coordinate is found by substituting the x coordinate into the parabola's equation and evaluating the function at this value of x. After that, the steps are very similar to what we did in the last example. To graph this function, first determine whether the parabola opens up or down. And by the way, that works exactly the same as if it was written in standard form. This value of a is actually the same as the value of a in standard form. Then determine the vertex of the parabola, and in this case you have to use the formula negative b over 2a for the x coordinate. Then you find the x-intercepts by solving f of x equals 0. And in that case you're either going to have to factor to find the solutions of that equation, or you're going to have to use the quadratic formula. Find the y-intercept by computing f of 0. And in this case, there's a shortcut. If you take the equation f of x equals ax squared plus bx plus c and substitute x equals 0, the only thing you're going to be left with is c. So the constant term in the function's equation, the y-intercept is c, and the parabola passes through the point 0, c. And then plot all those points and draw your parabola. So here is the next example. We're graphing the quadratic function f of x equals negative x squared plus 4x plus 1. Once again, a is negative 1, which is, of course, a negative number. So the parabola opens down. The vertex is 2, 5. There are a couple things here that I'm going to explain on the tablet, and then we'll come back and look at the graph. Okay, the x-intercepts in this case come out to be nasty numbers. You see them right there, approximately negative 0.24 and approximately 4.24. Those come from the quadratic formula. This one, I think, you might be able to see just by looking at the function. If you replace x with 0, this term goes away, this term goes away, you're just left with the 1. All right, so let's switch over to the tablet and look at steps 2 and 3 this time. Starting with the vertex. So our function is f of x equals negative x squared plus 4x plus 1. So a is negative 1 and b is 4. And of course c is 1, but in the vertex formula you don't have to use c. All right, so negative b over 2a, which is the x coordinate of my vertex, is going to be negative 4 divided by 2 times negative 1. 2 times negative 1 is negative 2. So what we have here is negative 2, which is 2. So that's how the negative b over 2a thing works. And then to find the y coordinate, you just substitute that value back into the function. So it's saying to do f of negative b over 2a. Well, we just figured out that negative b over 2a is negative 2. So I'm going to take my quadratic function, which is negative x squared plus 4x plus 1, and I am going to substitute negative 2 for x, and that is going to give me negative 4. Let's see, wait a minute. No, hold on a second. Okay, I see where I messed up. Of course, the x-coordinate of the vertex came out to be 2. It didn't come out to be negative 2. Sorry about that. Let's get rid of this negative. Waste too much stuff there. Okay. All right. Okay. So this is f of 2. We'll get all that right here in a second. Okay. F of 2 is going to look like this. Now we got it. See, I did this problem ahead of time and I knew it wasn't looking right. There we go. So when you substitute 2 into this function, you get negative 2 squared plus 4 times 2 plus 1, which is negative 4 plus 8 plus 1, which comes out to 5. So that's how we got 2, 5. Okay. And then in step 3, we found the x-intercepts. The function was f of x equals negative x squared plus 4x plus 1. So this time I will need the number c. A is negative 1, b is 4, c is 1. So using my quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That is going to give me okay, b is 4, b is still 4, a is negative 1, c is 1, a is negative 1. All right, so that's going to be negative 4 plus or minus, what do we have here? 16 plus 4 is 20, and that's all over negative 2. So depending on what kind of problem you're doing, you might want to find an exact or the exact values of those two numbers. In this case, we're just trying to draw a graph, so really approximate numbers will be better. So you can just put these into the calculator. And let me just remind you, hopefully you know this by now. When you go to do this on your calculator, one time you do it with plus, one time you do it with minus, you're going to have to put the negative 4 plus 20 in parentheses. Oops. And don't forget the divide by. That's kind of important. Negative 4 minus the square root of 20 divided by negative 2. This must be the one that comes out to, and you should do this on your calculator right now. Don't take my word for it. That must be the one that's approximately 4.24, and this must be the one that is approximately negative 0.24. All right, so now I think we're ready to go back to the presentation. And you put all that together in your graph, and this is what you end up with. There's the vertex at 2, 5. Here is the y-intercept at 0, 1. There's the negative 0.24. There's the 4.24. All right. Minimum and maximum of a quadratic function. Consider the quadratic function f of x equals ax squared plus bx plus c. If a is greater than 0, which you know means the parabola opens up, then this function is going to have a minimum value at the point where x equals negative b over 2a, because this point right here is a lowest point. That's where the minimum comes from. And you know that that point is the vertex, so it has these coordinates. Now, when you're doing problems involving the minimum or maximum value of a quadratic function, you have to pay attention to the question that's being asked. Sometimes they will ask you for the x value by saying something like, where does the minimum value occur? If they ask you what is the minimum value, they're looking for a y value. And then similarly, if a is less than 0, that means the parabola opens down. And in that case, your vertex represents a maximum value. All right, so let's see what we have here. Oh, in each case, the value of x equals negative b over 2a gives the location of the minimum or maximum value, and the value of y, which is f of negative b over 2a, gives you that minimum or maximum value. All right, so here's an example, and this one is all done out in the presentation, so I'm not going to have to switch over to the tablet. Consider the quadratic function f of x equals 4x squared minus 16x plus 1,000. They want us to determine without graphing whether the function has a minimum value or a maximum value. Oops, okay, and that's all they're asking right now. I thought there was, I think there is another question coming up a little later. All right, so just look at the value of a, right? A is 4, which is positive. That means this parabola opens up, and that means you have a minimum value, right? All right, parabola opens up. That means you have a lowest point on the parabola. That lowest point represents a minimum value. So the next question is, find the minimum or maximum value and determine where it occurs. So this is exactly what I was talking about a minute ago. Find the minimum or maximum value. That's going to be the y value. Determine where it occurs is going to be the x value. So we'll actually answer that second question first. All right, so we have a equals 4, b equals negative 16, c equals 1,000, which means negative b over 2a comes out to negative 16 over 2 times 4, which is 16 divided by 8, which is 2. So and we already decided this was a minimum. So the minimum value occurs at x equals 2. And the minimum value is f of 2, which is 4 times 2 squared minus 16 times 2 plus 1,000. That comes out to 984. So the minimum value of this function is 984. All right. And the last question is to identify the function's domain and range without graphing. I always have a little trouble explaining this problem without drawing a graph. I'm going to try to do it, and then I think I'm allowed to draw you a picture if I'm explaining it to you. All right, but you should ideally be able to answer this question going forward without drawing a graph. So picture in your mind the graph of this function, and really the important thing is where is the vertex, and then does the parabola open up or down? Okay, I think I'm going to have to draw this picture in order to explain this to you. So let me get the tablet up here. Okay, I'm not going to bother drawing a particularly pretty graph of this. Really, the important thing is, like I said, where is the vertex? We know it is at the point 2, 984. And then we know the parabola opens up. All right, so in one of the sections in chapter 1, I can't remember for sure, but I think in chapter 1 we might have talked about reading the domain and the range of a function from the graph. I think we did that. And the way that I like to explain that is for the domain, you just squash the graph onto the x-axis. And if you squash this graph onto the x-axis, it would hit the entire x-axis because the parabola is going forever to the left and forever to the right. So that means the domain is all real numbers. If you squash the graph onto the y-axis, you are not going to hit all real numbers. You're going to hit starting here at 984 and going up. So the range is all real numbers greater than or equal to 984. Whoops, 984. Okay. So yes, I know I cheated drawing the graph, but I really don't know how to explain it without drawing the picture. Okay, but hopefully you get the idea. All right, so here's their explanation of that problem that we just did. Like all quadratic functions, the domain is all real numbers. So that's another shortcut. Quadratic functions and what we're going to get into talking about in the next section, polynomial functions, domain is always all real numbers. And then the business that we talked about with the vertex. All right, so we'll end this section by talking about strategy for solving problems involving maximizing or minimizing quadratic functions. Step 1, read the problem carefully and decide which quantity is to be maximized or minimized. Then use the conditions of the problem to express the quantity as a function in one variable. And then rewrite the function in the form f of x equals ax squared plus bx plus c. Calculate the vertex of that function, really negative b over 2a. And like we talked about before, you can figure out whether that's going to give you a minimum or a maximum. And remember to answer the question posed in the problem. So I actually have two examples. They're pretty similar to each other. So I'm going to do the first one. And then when we get to the second one, I'm going to ask you to pause the video, try it yourself, and then come back and we'll compare notes. Okay, this is a classic problem. I bet you will do this again when you get to calculus. You have 120 feet of fencing to enclose a rectangular region. Find the dimensions of the rectangle that maximize the enclosed area and what is the maximum area. Okay, so I'm going to switch over to the tablet. All right, here we go. So we're trying to fence off a rectangular region using 120 feet of fence. Okay. So I am going to introduce a variable into this thing, and I think I'll switch over to, I don't think I want to do this whole problem in green. All right. Let's let x be the width of the region. Like that. Okay, so remember, the total amount of fence is 120 feet. So I think the simplest way to do this might be like this. And we'll say y is the length of the region. Might have made more sense to do it the other way around, but that's okay. Okay, so we want to maximize the area, which is the length times the width. In this case, that's x times y. But there is a condition placed on x and y, which is that the perimeter of this rectangle has to be 120 feet, right? So we know that, let's say, given 2x plus 2y equals 120. So I'm going to use that equation to write my area as a function of one variable. And I'm going to do that by solving this equation for, let's say, y. It really doesn't matter. Subtract 2x from both sides. That gives me 2y equals negative 2x plus 120. Divide everybody by 2. That gives me y equals negative x plus 60. Okay. So here's what we have. We have the area is x times y. But now I can write that as a function of just the one variable x by substituting this expression for y. So instead, I'm going to put this x stays put, but then instead of putting y, I'm going to put negative x plus 60. So that gives me the area of the rectangle as a function of just x. Let's write it in the normal form by distributing the x. That's going to be negative x squared plus 60x. So now I see an a and a b. A is negative 1. B is 60. Since a is less than 0, parabola opens down, which means we have a maximum value. That's a good thing because they told us there was going to be a maximum value. All right, so the maximum is going to occur when x is negative b over 2a, which is negative 60 over 2 times negative 1, which is 30. So what was the question again? Well, there were two questions, actually. One question was to find the dimensions of the rectangle with the largest area. So I have one of those dimensions. X is what we were calling the width. And then the length, which we called y, is given by negative x plus 60, which comes out to, oh, look at that. It also comes out to 30. All right, so if you have a given amount of fencing and you need to use that fencing to enclose all 4 sides of a region to make a rectangle, the best way to do that is to make the region a square. Okay. Now, we've only answered one of their questions. The other question is, what is the maximum area? That's easy. We know the width is 30. We know the length is 30. That comes out to 900 square feet. All right. This kind of problem is important in calculus. This is called optimization when you get to calculus, and you learn how to do it with other kinds of functions besides just quadratic functions. All right. So now, going back to the presentation, as promised, I would like you to try this one. Suppose now that one side of the rectangular region will be alongside a barn. So no fence is needed on that side. What should the dimensions of the region be to maximize the area? And what is the maximum area? So please pause the video, give yourself a chance to figure that out, and then we'll come back and compare notes. Okay, so I went ahead and got this thing started. Here is my region up against the barn. So the difference with this problem, you start to see it when you get down here. We're still trying to maximize area, which is still x times y. However, what we call the constraint in this problem is that the amount of fence still has to add up to 120, but this time that's not the whole perimeter of the rectangle, right? In this case, the amount of fence is going to be given by 2x plus y, only one y, right? Because I don't have to put any fence over here, okay? So now I'm going to do the same thing that I did in the previous problem. I'm going to solve this for y, and that's going to give me y equals negative 2x plus 120. So when I write my area function, y is going to get replaced with negative 2x plus 120, which means my area function now is negative 2x squared plus 120x. All right, so the value of x that's going to make that a maximum, and again it is a maximum because this thing is negative, is going to be negative 120 divided by 2 times negative 2. Oh, look at that, it still comes out to 30. Okay. So the optimal width for this region is still 30 feet. However, that makes the optimal length not 30, but 60. So making the region a square is no longer the best thing to do. You actually want to make this a 30 by 60 rectangle. So there are your dimensions, 30 feet by 60 feet, and the maximum area is 30 times 60, which is 1,800 square feet. You can double your area if you're allowed to put one side of the region up against a barn or a river or something like that. All right, so we talked about quite a bit of stuff in this section, but that's the end of it. So we'll see you next time in section 2.3.